Hello, I'm Ophir, and I'm with my friend Ivan here.
Hello.
And I'm going to provide a brief overview of a bunch of stuff I know about getting transformer to extrapolate to longer sequences than they were trained on, and how to correctly evaluate transformer models that were trained on different input links. Okay, so usually when we have a transformer, we feed it words, right? And so like the first word is going to be like, the cat is, I don't know, black. And in the original kind of transformer, the first thing that we would do is we would turn each one of these words into a word embedding, some vector representation of this word.
Mm-hmm.
But then we would also have vector representation. So for each one of these words, we have a vector of 1,000 floats that represent this word. And we're now going to also have a vector to represent position ID 1, and a vector to represent position ID 2, and a vector to represent 3 and 4, and so on. Right? And so this is, it's not the number one, it's a vector for one. Let's mark it like this. And this is a vector that represents the second position, and so on.
Mm-hmm.
And then before we would feed all of this into the transformer, we would add the representation of the to the representation of 1, the representation of cat to the representation of 2, and so on. And so now, when we feed this into the transformer, we're telling the transformer, hey, I have the word the at position 1 and the word cat at position 2 and is at position 3 and so on. Then we feed this all into a transformer. And when the original transformer paper was written, they had kind of two alternatives for how to compute these position representations. So one of them is kind of the simpler one. It's just called learned position representations. So you just initialize each one of these position representations randomly,
Mm-hmm.
and you just learn a certain representation for 1, for 2, for 3, and for 4. The other alternative that they propose is called sinusoidal position embeddings, and those are non-parametric because they're not learned. There's nothing to learn there.
Mm-hmm.
It's just a function that they defined where you give it an ID and it returns a dense vector that represents that ID.
Yeah.
So there's nothing to learn. So that's kind of the position embeddings that were proposed with the original transformer paper. We're going to come back to this, but before we come back to it, I'm going to talk about what extrapolation means. So when we train a language model, what we do is we gather lots of text from the internet and from books and video transcripts. We gather lots of text, and we have one long document, and then we concatenate it to another document, concatenate to another document, to another document. And then we have this really, really, really long continuous string made up of different documents that's like billions of tokens long, right? And we want to train our transformer on it. But when we have a transformer model, it's limited, right? We have GPUs that have a finite amount of memory. And so what we do when we have a transformer model is we take a chunk of text, we feed it into the transformer, and then we have a loss function. So let's say we take a chunk of 1,000 words, we take these same 1,000 words, but just moved one word to the right, and those are the targets, right? We have 1,000 inputs and 1,000 outputs. And we'd like to be able to take this really long string of billions of tokens and just feed the whole thing into this huge transformer, right? And then ask it to predict this sequence again, but moved one word to the right, right? That's what we'd like to be able to do. But GPUs have a finite amount of memory, and so we cannot do this. We're going to run out of memory. GPUs can only handle right between like 4,000 or 8,000 or maybe like 16,000 tokens at once. So, you know, if OpenAI is training a new model now, they have to kind of decide on a train sequence length. And let's say that training sequence length is 4,000 tokens. So we have 4,000 tokens that we're putting in, and we're outputting 4,000 tokens. We're trying to predict the next word at each time step. The question that immediately arises is, I've trained this model on 4,000 tokens, but now I'm writing a code file, and I'm using like, you know, Copilot or something to help me predict the next word. And I just got to index 4,000 in my code file. Can my language model that I've trained on 4,000 tokens, can it predict the next word? Or I train a language model on 4,000 tokens, but I'd like to generate a 5,000 word story. Can I do that? Or I train a language model on 4,000 words, but I have a 10,000 word New York Times article. Can I summarize it? So that is the extrapolation problem. And that's what I explored in the ALiBi paper. And now I'll talk about some results from ALiBi. And just the one thing that I didn't say is that when OpenAI wants to train a new language model, they have this sequence of, you know, billions of tokens from the web. What they do is they decide on a training length, 4,000, and then they chop up their big sequence into chunks of 4,000, and then at every iteration you just pick, you know, a random chunk, you train on that, and you pick another random chunk, another random chunk. And so on. You're just constantly training on random chunks of 4,000 tokens. Okay, so what we discovered in ALiBi is that when you do this thing with transformers, where you have a sentence, and then to every word you add a position representation, is that transformers, so we're feeding in these position representations not because it's really important right now that cat is at 2 or that is at 3. We're feeding in these representations because we want the model to know what the relative ordering is. We want it to know that cat is appearing right before, is appearing one word before is, and the is appearing 2 words before is. But what we discovered in ALiBi is that transformers overfit to these position representations, and therefore they cannot extrapolate to longer sequences. So we gave the transformers these position representations because we wanted them to understand relative distances, but what ended up happening is that the transformer was like, okay, cat right now is at position 2, here's what I need to learn about position 2. Is right now is at position 3, here's what I know about position 3. Like, they did this really dumb thing where they're kind of overfitting to specific representations. And then when you give them, let's say you train your language model on 1,000 words, you suddenly give it word 1,001. It's like, 1,001? I've never seen position embedding 1,001. And it explodes. It's like, it becomes really, really dumb. So we show in ALiBi that at 1,001 it can kind of handle stuff, But then when you get beyond, like, 1,000 and 100 or whatever, it becomes really, really dumb. It's just these position representations are just, it's never seen them before, and it doesn't understand that 1,001 it's just one more than 1,000, so it just explodes. So we showed that with regular transformers, they can just not extrapolate. The absolute, so if you learn a position representation for every index with absolute position embeddings, you just cannot extrapolate. So that's what GPT-3 used. So it just doesn't have a position representation for 1,001 if it was trained on 1,000 tokens. With Sinusoidal, you can have position representations, but you won't get a runtime exception, but like the transformer won't understand them. Okay, so how did we solve this? And the kind of general way to solve this is by doing something called relative position embeddings. So instead of adding position representations, what we did in ALiBi is that we do not have any position representations anymore. We just change the attention computation. So if you have, like, the cat is brown, and right, usually you're attending between, when you're trying to predict the next word that's going to come here to the right, you're using this as your query, and you're looking at everything, at all the other words as your keys, and you're computing attention representations between all of these pairings, right? And what we did with ALiBi is the further away a word is, so we're computing, so here the computation is Q times, let's call this key 3, and then here the computation is Q times key 2, and this is Q times key 1. So what we did was, instead of just computing these attention values like normal, this is what you normally do, we just add this bias that increases the further away a pair of words is from each other. So here they're just one word away from each other, so we're going to subtract 1 times this bias. Here there are 2 words away, so we're going to subtract 2 times this bias, which is just, B is just a number. And here we're going to subtract 3 times this bias. And that's it. It kind of allows transformer models to extrapolate, but not really. That's ALiBi. Okay, now I'll talk a bit about evaluating these models. Okay. So how do we evaluate language models? So I think the best way to evaluate language models is on downstream tasks. And thankfully, that's become like the de facto way to do it. And it's pretty good. It's probably the best. But another way to evaluate language models is by computing perplexity. And there's multiple different ways to do it. And it can get kind of confusing. So here are like the kind of ways to do perplexity evaluation. So we now have a trained language model, and we want a perplexity value. And so what we do is, again, we collect a bunch of documents. We do this before training. We collect a bunch of documents that we take away from the training set. So now we have a bunch of documents that the model has never, ever seen. And again, we concatenate them into one long sequence. And again, this is going to be maybe millions of tokens long, so we can't feed it in to the transformer all at once. So the first way to evaluate perplexity, and in the short form paper we call it non-overlapping evaluation, is to, again, if our training length is 4,000, we divide our sequence into chunks of 4,000 tokens, and then we compute the perplexity for this chunk, and then the perplexity for this chunk separately, and for the third chunk, and fourth chunk, and so on. Perplexity is just a fancy word for the average probability that we assign to the correct next word. So language models are always trying to predict the next word, and you can see what probability they gave to the correct next word. You just average it out over the entire sequence. The place where this can be problematic is if you have two models that were trained on different input links. So let's say you have a llama model that was trained on 4,000 words, and you have another llama model that was trained on 8,000 words, and you have the same development set that you'd like to compute these perplexity numbers for. But now, when you chop it up for the bigger llama model, there's going to be less chopping, right? Because the chunks are much longer. And if you just naively compute perplexity on this chunk here, and then on this chunk, and then on this chunk, and so on, you'll get better perplexity for the 8,000 model, basically always. And in our short form paper, we show that this is not a fair way to compare models because of something we call the early token curse. If you look at your model's outputs, you'll see that it always really, really struggles, and this makes a lot of sense, it always really, really struggles to predict the first few tokens. Like the first 5 tokens are really, really hard to predict because you don't have any context there. And so if you're doing this non-overlapping comparison between two models, and this model has sequence lengths that are twice as big, it's not fair. You're giving it this longer model, it has a much easier task to accomplish. It has much less of these early token issues to deal with. It has half as many. And so it's basically always going to win. And so this isn't a great way to evaluate perplexity. The better way to evaluate perplexity is called sliding window evaluation. And here's how it works. So if these black lines are words, so non-overlapping evaluation, let's say we have a model that can read 3 words at once. So if you do non-overlapping evaluation, you would evaluate the perplexity for these 3 words, and then you would evaluate the perplexity for these 3 words, and then these 3 words, and so on. And again, as I said, like it's unfair because it always struggles with this first word here, and then the first word here, and then the first word here. Constantly has to struggle with these really hard challenges of predicting a word with 1 word of context. It's really, really hard, or with little context. It's a sliding window evaluation, which was invented by Baevsky and Ali in 2017, is going to do something much smarter. And here's what it does. So the first iteration, it evaluates these 3 words, just like we did before. But in the second iteration, it feeds forwards through these 3 words, but it only asks for the probability from this word. So it's getting probabilities for these words, but it tosses them out because we already have the probabilities from here. And then in the third evaluation run, it feeds forward through these 3 words, and it only asks for the probability value that was made here, not here and here. And then so on and so forth. Sorry, no, minus here. Yeah, so this is sliding window evaluation, and if you compare models of different that were trained on different lengths with sliding window evaluation, it's a totally fair way to compare different models. And a really cool fact that we discovered in the short format paper, we trained models on different sequence lengths from between like, I don't know, 32 tokens to like 3,000 tokens. And what we discovered was that at the time, models trained on 1,000 tokens were actually just as good as models trained on 3,000 tokens, as seen by sliding window evaluation, which is the correct way to evaluate these models. So anyways, now people have these extrapolation tricks, like this person posted this llama extrapolation trick, and he initially evaluated it with non-overlapping evaluation. It was like, oh, the llama trick works, this model is better. But then when people did better evaluation, they showed that it actually doesn't work. The llama extrapolation trick, if you don't fine-tune it, just doesn't work. It doesn't lead to a better model. Yeah, the other stuff, I think, anyways, when we, at the end of the ALiBi paper, we showed that models built using ALiBi extrapolate as judged by non-overlapping evaluation, but if you use the more accurate sliding window evaluation, ALiBi models actually, they don't extrapolate, they stay at the same quality. And I think that that's basically the state of the art right now. Nobody has figured out how to build models that can consume sequence, that can effectively use more context than they observed during training. That's an unsolved problem. If you want to effectively use N tokens during inference, you have to train or fine-tune on N tokens. If you train on 8,000, you will only understand 8,000 tokens at inference. You will not understand more than 8,000. The best you can do, that's the best you can do. You cannot understand more than what you saw. There's still advantages to methods like ALiBi, but you can never understand more tokens than what you saw during training, at least at this point. Okay.
Makes sense. I have a very basic transformers question.
Yes.
So in your sliding window, when you feed in these three, this is during inference first of all, right?
This is inference, yeah.
Yeah, so you feed in these three, right?
Yeah.
What do you get? Do you get like a prediction for what is your output?
Yeah. So when you feed in this word, you get an output which is a distribution over the output, which is the next.
Finish that.
You get a distribution which represents the model's prediction for the next word. So you can't really feed in three words. At inference. Okay. So there's two types of inference. There's inference when I'm trying to generate a sentence, and there's inference when I'm trying to compute perplexity. And those two types of inference are very different.
Okay, I think that's what I.
Okay. That's what you were. Okay.
So basically, when you're doing perplexity.
I'll explain.
Okay. Yeah.
When you're trying to interact with the user, when the user is just giving you a prompt and you're trying to fill, you're trying to give them something, you have to predict word by word.
Yeah.
You have to predict the first word and then sample from that, predict the second word, sample, predict the third word, and so on. If you're trying to evaluate perplexity, it's this kind of weird edge case where you're actually not using the model to make predictions because you exactly know what text you're feeding. The only thing that you're asking the model to do is kind of give you a probability value for the sequence, and then you can actually input multiple words in parallel. So now we're feeding in these three words in parallel, but the transformer, there's a lot of sides here. The transformer internally, so the only thing that's happening in parallel is the computation, but internally there's a causal mask. So even though we're computing three outputs in parallel, the transformer at each point thinks that it's doing the inference time thing of seeing one word at a time. Because when it's making this prediction, that first output prediction, it can only see the first input. When it's making the second output prediction, it can only see the first two inputs. And when it's making the third, it can only see. The first token cannot see anything. The second token can see first. The third token can see the first two, right? Yeah. So you're doing these three computations in parallel. Yeah. But they're each kind of, it's just a computation thing in like each of these computations can only see the past and kind of acts as if it was independent.
During perplexity inference.
Exactly.
And during user inference, as you called it.
Let's call it generation.
Generation. Yeah. What does it mean to be feeding, say you're feeding a query, which is multiple, or you're feeding a question, which is multiple tokens, right?
You're feeding a question which is
which
correct.
I know what these are because I type them in.
Correct. So you're doing the same thing.
Oh,
that we're
you're doing the
right
same
now.
thing.
You're doing the same
Uh-huh.
Perplexity thing, where you're feeding in 20 tokens at once.
And
Exactly.
then you're only interested. So how does the token consider the sequence of how does the transformer consider the sequence of these tokens?
How does the transformer consider the sequence? What do you mean?
Or I guess maybe this bit is like this causal mask is what
Yeah, exactly.
it
So
means for
if you have a question for the transformer that's like 20 tokens,
yeah.
it encodes all those 20 tokens at once, but each of these 20 tokens can only see the past when it's being encoded.
Yeah, of course. That makes sense.
Yep, and then it generates one at a time.
Yeah. Okay, that makes
It
sense.
generates the
Yeah.
answer one at a time.
And when you're doing Perplexity, it generates. You still feed it 20 or whatever your context
Yeah.
thing
yeah,
is.
yeah.
And then what does it give you out?
So at each time step, it gives you a distribution over what it thinks the next
But
word
just
is.
one. Even when you're
One-
doing Perplexity inference.
So when you're doing the Perplexity computation, you're feeding in, let's say, 4,000 words.
Mm-hmm.
At every index, it returns a distribution, right? So the first
okay,
word.
that's what I was asking. Yeah.
So it returns a distribution,
Yeah.
and then you actually dump that. You don't need that whole
Yeah,
distribution,
of
right?
course, yeah.
The first word that we fed in is the,
Yeah.
and we wanted the next. Our second word is cat, right?
Yeah.
So I feed in the word the, and it gives me a distribution over the next word. I toss out everything except the probability it gave for cat.
Yeah.
That I save, and that's part of my perplexity calculation.
Yeah.
And the higher it is, the better my perplexity will be. And then
Yeah.
the first two words are the cat, and the word I want to see is, it gives me again a distribution.
Mm-hmm.
The word I want to see is. I toss away all the probability values except the one given for is,
Mm-hmm.
and that's part of my perplexity computation.
Oh, because you have you have ground truth. That's
Exactly.
the only difference.
Yeah, your ground truth is just the correct next
But when
word.
you have fed in, there's no other difference between Perplexity and generation. So like every time you're generating and you give it like 3 tokens, it would
Okay.
always give you what it thinks the probability for. Say you have the cat is.
Right.
It would always give you a probability for what it thinks the word at cat should be, and
Right.
it will give you a probability for what it thinks the word at is
Yeah,
should be, and then
yeah.
give you a probability for the fourth.
Yep.
Okay, that's what I was
So when
asking.
you're
yeah.
feeding in a prompt.
Yeah. Oh, prompt. That's the word I was.
So when you're feeding in a prompt, it will feed forward through the entire prompt, and at each step, it will tell you what it thinks the next
Yeah.
word is. But of course, you don't. If you're feeding in a prompt, if you're asking the transformer question that's 50 tokens,
Yeah.
it'll make predictions about the next word for the first 50 tokens. You dump all of that
Yeah, of
away.
course.
It's total
Okay.
trash.
Yeah.
You only take its last prediction. That's what
Yeah,
you need.
yeah.
And then you sample from that. It makes one prediction.
that-
you take it.
Okay,
Yeah.
so that's
Yeah.
exactly how I thought it was. Okay,
Okay.
so I get it now.
Other questions about perplexity, length, anything?
No.
Okay. Thank you very much.